What we're going to look at is the Sn1 substitution of any type of allylic substrate. Now, I want you to be aware this works with primary, secondary, and tertiary because you're not really making a single carbocation at one location, and most of you are going to be very hesitant to do this with something that is primary because you've been told over and over again primary carbocations don't exist. But this doesn't produce a primary carbocation. It's going to produce an allylic carbocation, which means that it has resonance. So allylic carbocations are always more stable than something that does not have resonance. Don't get stuck when these things look primary. And I'm going to draw one on a primary carbon for this reason. And when you do these, you're going to be adding some sort of a nucleophile if you're trying to do a substitution. So I'm going to use one of our favorites, a thiolate, CH3S-. And I'm going to pair that up with a sodium. The sodium is just a spectator. We don't really care about it at all. And since we are trying to get this to go by an Sn1 pathway and not an Sn2, because if you do Sn2 it's just going to be what you're normally used to, you need to be using a polar aprotic or a polar protic solvent, something that is capable of hydrogen bonding. So use something like an alcohol or an amine. I'm going to use methanol. Now in class we talked about the fact that you're going to get two products, and in order to know which one's major and which one's minor, you need to be hot or cold in the reaction conditions. And so I'll just say hot or cold on the bottom of the arrow. Typically if you want something cold, for instance, we use dry ice and acetone to make a slurry, and that's kept at like -76°C. Or you could heat the reaction up on a hot plate to get it nice and hot. Depends on what you want. This time I'm going to keep it cold, and so I'm just going to write cold on the bottom of the arrow. And we'll talk about what that means. But you can do this hot or cold, and that does influence which product is the major one and which one is the minor one. So the first step of this mechanism is the slow step. It is the step where we form the carbocation. Now, in this step, you'd have to break this carbon-bromine bond, and bromine takes those electrons because bromine is more electronegative. Typically, you don't form a primary carbocation. But again, this isn't a primary carbocation that you are making. It's an allylic carbocation. So there is some resonance associated with it. This is one of the resonance structures, the one you would expect to draw right off the bat. But because it is an allylic system, and you have this conjugated pi system, there is resonance delocalization of this positive charge onto the tertiary carbon. So this is a more stable carbocation than any of the ones we've seen previously. It's not a primary carbocation, it's not a secondary carbocation, it's not a tertiary carbocation. It has resonance delocalization. And so whenever you have more resonance, you've got more stability, and that's more likely to happen. Now bromide is still hanging around. It's a spectator, and it's going to just hang out with that sodium that was paired up with our nucleophile. They're just spectators. Okay, so we now have our nucleophile. Now this nucleophile can add to either one of these two carbons, because both of them have some positive character. Now the way you know which one adds to more of the time is temperature. When you're operating under kinetic control, which is what we are doing here, the cold conditions, you want to be in the more favored state. And so in this case you would prefer to be more like the carbocation there on the right because it's more stable. Now again, this is one carbocation, but that's the major contributor to the resonance. You'd rather be that structure, the one there on the right, because that's where the positive charge is on a tertiary one. So this is more likely, and you don't have enough energy to add as often to the resonance structure where the positive charge is on the primary carbon. It will add to both. So in red here I'm showing the major product under cold conditions. That would be the kinetic product because you favor the one that has the more stable resonance structure. And in this case, the minor product would be the addition to that primary carbon. But both products are going to occur. So in red here, I'm going to show the kinetic product of our reaction. And this would be the major product when things are cold. The thermodynamic, oops, I think I said that wrong. That one is the thermodynamic product. Whoops. This one is the kinetic product. So I'll write that down for you, since I said that wrong. The one here in blue is the kinetic product. And it is favored under cold conditions. The one up here in red is the thermodynamic product. Okay, now as you look at these, the kinetic product is the result of adding to the tertiary resonance structure, and it would be the major product when things are cold like we have right now. The one in red up there on the top is the thermodynamic product, and it would be the major product when you heat things up. Now, the way I know that the one in red, the thermodynamic product, is the thermodynamic product is because it is chemically more stable. And the way that I know that is by looking at the placement of the double bond in both of these two structures. The one in red, the double bond is a tertiary alkene, or tri-substituted alkene. And the one down there in blue is a monosubstituted alkene. So the tertiary alkene is more stable because it's more substituted. And on the bottom is monosubstituted, so it's less stable, and therefore it's more reactive. So depending on which one you want to be the major product, you would watch the temperature. Both of them are always going to form. You can't say one's going to form at one time and not the other time. They always both form. But the temperature is the key to knowing which one is the major product.